Hi students, this is Alex here. In this video, we are going to verify Stoke's theorem for the given f vector over a square region in the xy plane bounded by the vertices 1, 0, minus 1, 0, 0, 1 and 0, minus 1. Let's write the Stoke's theorem, which is integral over C f vector dot dr vector is equal to double integral over the region S del cross f vector dot n cap ds. Now we are going to take a small diagram for the given square region in the xy plane. So we take x-axis, y-axis, this is our x, this is our y, and we have 4 points 1, 0. So 1, 0 I take it here, which is point A. Then minus 1, 0 will be somewhere here. So this is minus 1, 0. Let's take this as point B. Or we take the points in the order, that is A, B, C in a continuous order. Now the third point 0, 1 will be somewhere here, 0, 1. Then 0, minus 1 will be somewhere here, 0, minus 1. So this is A, and let this be B, and this is C, and this is D. So this is our square region. So let's join AB, then BC, then CD, and finally DA. So this is our square region under consideration. Now we have to get the equation for each line, that is AB, BC, CD and DA. So let's write equation of AB. We have 2 points, A is 1, 0 and B is 0, 1. So we have 2-point formula, 1 y minus y1 by y2 minus y1 equal to x minus x1 by x2 minus x1. So we can name any point as x1, y1 and we can substitute in the formula. So I have named x1, y1 and x2, y2. Now this is y minus y1 is 0, y2 minus y1 is y minus 0, then x minus x1 is 1, x2 is 0 and this is minus 1. Then finally this is y by 1 equal to x minus 1 by minus 1. So after cross multiplication we get minus y equal to x minus 1. From this I take x plus y equal to 1. So this is our equation, x plus y equal to 1. In the same way I have to find for BC, that is we have 0, 1 and minus 1, 0. So we are going to take equation of BC. Again let's name this as x1, y1, x2, y2 and using the same 2-point formula, y minus y1 by y2 minus y1 equal to x minus x1 by x2 minus x1. So from this y minus 1 by minus 1 is equal to x by minus 1. So we can cancel this. After cross multiplication y minus 1 is equal to x, and when I take this everything on one side, that is x, then minus y equal to minus 1. So this is our equation, x minus y equal to minus 1. In the same way for CD it is minus 1, 0, 0, minus 1. So minus 1, 0 and 0, minus 1. We are going to find equation of the line CD. Once again let's name this as x1, y1, x2 y2. So y minus y1 by y2 minus y1 equal to x minus x1. So it become plus 1 by x2 minus x1. So from this we get y by minus 1 is equal to x plus 1 by 1. On cross multiplication we get y equal to minus x minus 1. Then again x plus y equal to minus 1. So this equation is x plus y equal to minus 1. And the last one is dA 0 comma minus 1 and 1 comma 0. That is for equation of dA. This is as usual x1 y1 x2 y2. So y minus y1 by y2 minus y1 equal to x minus x1 by x2 minus x1. So finally this is y plus 1 by 1 equal to x by 1. On cross multiplication y plus 1 is equal to x. So x minus y equal to 1. So this is x minus y equal to 1. So we got the equation for all the 4 boundaries. Now we are going to take the left hand side of the Stokes theorem. In left hand side we need f vector dot dr, and dr vector is dx I cap plus dy j cap plus dz k cap. So f vector dot dr vector becomes, we have to do dot product of the f vector given in the question with this dr vector. So corresponding I and I, if I multiply, it is xy dx plus xy square dy, and there is no k component in f vector. So this is our f vector dot dr vector. Now in LHS we have integral over C. It is taken into 4 parts. One is integral over AB, then BC, then CD and DA. Now coming to the first part, AB, integral over AB is integral f dot d is xy dx plus xy square dy, and its equation is x plus y is equal to 1. So x plus y equal to 1. Let's take what is x from this, which is 1 minus y, and dx is minus dy. So we have to substitute x and dx here. So integral x is 1 minus y into y as it is, and dx is minus dy. So into minus dy plus x is again 1 minus y into y square dy. Everything is dy. So let's take the limit of AB. So limit of AB is, you can see here the region, that is this line AB is here, and when I take a limit from A to B, the lowermost value and the uppermost value I have to take. This is y equal to 0 because it is on the x axis, and the uppermost value is 1 here. So the limit is from 0 to 1. So we take 0 to 1 here, and we are going to evaluate this. Before that, we simplify this further, and this part is minus y. When I multiply inside, minus y plus y square, and when I multiply y square inside, it is plus y square minus y cube into dy. So on integration, this is minus y square by 2. This is already 2y square, so 2y cube by 3, and this is y power 4 by 4, and we have limit from 0 to 1. When we substitute the upper limit, we get minus 1 by 2 plus 2 by 3 minus 1 by 4. LCM is 12. So this is minus 6 and plus 8 and minus 3. So totally this is minus 1 by 12. Now coming to the second part, BC, which is integral xy dx plus xy square dy, and BC equation is x minus y is equal to minus 1. So x minus y is equal to minus 1. From this, x is y minus 1 and dx is dy, and the limit for dy, that is for y, it is from B to C. So it starts from here and end at here. So the limit of y varies from 1. So the topmost value is 1 and the bottommost value is 0. So it is 1 to 0. So we have to take 1 to 0 and I have to replace every x and dx. So integral 1 to 0, x is y minus 1 into y and dy, and x is y minus 1 into y square dy. Now this is y square minus y, and this is plus y cube minus y square into dy. Limit is from 1 to 0. We can cancel minus y square plus y square. This is minus y square by 2 plus y power 4 by 4, and we have the limit from 1 to 0. When I use the upper limit, everything is 0. When I use the lower limit, it is minus 1 by 2 plus 1 by 4. On simplification, we get inside the bracket term as minus 1 by 4. There is a minus sign outside, so plus 1 by 4. Now coming to the third part, integral CD. So from this diagram, we can see CD, and the limit from C to D varies from 0 to minus 1. So it starts from 0 and end at minus 1. So we take this limit as 0 to minus 1, xy dx plus xy square dy, and we have to change everything in terms of y. The limit we have written, equation is x plus y is equal to minus 1. So it is x plus y equal to minus 1 and x is minus y minus 1 and dx is minus dy. So this becomes integral 0 to minus 1 minus y minus 1 into y, then dx is minus dy plus minus y minus 1 into y square dy as it is. So x alone we have replaced in the second term, and this becomes, after multiplying this inside, y square plus y, and this is minus y cube minus y square. You can cancel these two, and on integration we get y square by 2 minus y power 4 by 4, and the limit is from 0 to minus 1. When we use upper limit, it is 1 by 2 minus of 1 by 4. Lower limit, everything is 0. So totally this is 1 by 4. Then coming to the last part, which is dA, and in this the limit from D to A. So when it is from D to A, it goes something like this. So it varies from the lowermost minus 1 to 0. So minus 1 to 0 is our limit of y, and it is xy dx plus xy square dy, and its equation, we have it in the diagram, x minus y is equal to 1. So x minus y equal to 1. From this, x is y plus 1. So dx is dy. When we replace, it becomes x, which is 1, y plus 1 into y and dy. Again, it is x is y plus 1, then y square dy as it is. So totally So this one, integral minus 1 to 0, after multiplying inside y square plus y, and this is y cube plus y dy. Now when we integrate this y square, it is y cube by 3, and this is 2y, so this is 2y square by 2 after integration. Then the last part is y power 4 by 4, and we have the limit from minus 1 to 0. When we apply the upper limit, everything is 0. When we apply the lower limit, it is minus 1 by 3, and this becomes plus 1 and plus 1 by 4. Totally, sorry, a small correction. The last term is y square. So we cannot combine these two. Instead, we can combine the y square term alone. So let's integrate again. This is y square plus y and y cube plus y square. So y square and y square is 2y square. So 2y cube by 3 on integration. Y is y square by 2 and y power 3 is y power 4 by 4. So totally we have from limit minus 1 to 0. When we use the upper limit, everything is 0. When we use the lower limit, it is minus 2 by 3 plus 1 by 2 plus 1 by 4. On taking LCM, we get LCM is 12, and here it is minus 8 plus 6 plus 3, and this is 9 minus 8, 1 by 12, that is outside minus sign, so minus 1 by 12. So we completed all the 4 parts. We are going to add everything. So now integral over C, the first part AB, which we got it as minus 1 by 12. Let's write it here, minus 1 by 12 plus next part BC, which is minus 1 by 4. Sorry, BC is 1 by 4. So it is plus 1 by 4. Then CD is 1 by 4. So again plus 1 by 4, and DA, which we got as minus 1 by 12. So minus 1 by 12. So we can combine these two, which is minus 2 by 12, and we can combine these two, which is 2 by 4. On reducing this, minus 1 by 6 plus 1 by 2. So we can put into 3 to make common denominator. So 3 minus 1, which is 2 by 6, and totally it is 1 by 3. The complete LHS which we got is 1 by 3. Now coming to the right hand side of the Stokes theorem, we have double integral over the region S del cross F vector dot n cap ds. This is the F vector given in the question. So first let's calculate what is del cross F vector. For that we have to use determinant. First row is I cap, j cap, k cap, then del component dou by dou x, dou by dou y, dou by dou z, and F component which is xy, then xy square and 0. Now we are going to evaluate this determinant, and now this is I cap into, this is 0, and derivative of xy square with respect to z is 0. Then minus j cap, in the same way this is 0 and this also 0, and plus k cap into this derivative dou by dou x of this is only y square minus this derivative y is 1 and x is remaining as it is. So totally double integral over S del cross F is k cap into y square minus x, and n cap is perpendicular to xy, that is xy plane is k cap. So dot k cap, and ds is dx dy. So dx and dy. So instead of this we can write dx dy. So finally k dot k is 1. So double integral over s y square minus x into dx dy. Now if I take a horizontal strip for the limit, it is touching different boundaries. That is, when I move this from one place to another place, you can see from here it is touching AD and CD. But if I move up, it is touching AB and BC. So it is touching two different lines. So we have to split this into two parts. So I have to take this region separately as the region S1 and this as the region S2. So I'm going to write this as S1 and S2. So double integral over S1 y square minus x dx dy, then double integral over S2 y square minus x dx dy. Now double integral y square minus x with respect to x, then with respect to y. So S1 region, x limit if I take a horizontal strip here, the limit of x I have to take from this equation. X here is, when I take the y to the other side, y minus 1, and here when I take x, it is 1 minus y. So 1 minus y, this is y minus 1. So what I can do is, I can write it as y minus 1 to 1 minus y for the first part, y minus 1 to 1 minus y. And if I take a vertical strip for this region, the lowermost is 0 and uppermost is 1 for y. That is from 0 to 1. This one we can rewrite, that is integral 0 to 1 integral, we can take the minus sign common, so minus of 1 minus y to plus of 1 minus y. So the reason for writing this is to make the integration easier. We can apply the property. When I integrate this with respect to x, we have y square, which is a constant. So the constant y square will become y square into x, and this becomes minus x square by 2. But if I take this term alone, this is the odd function. In previous videos we have done what is even function and odd function. When there is an odd function, when limit is from minus a to a, f of x dx, it becomes 0. So if I integrate this as minus x square by 2, then I put upper limit minus of then lower limit, it becomes 0. So using this property, that becomes 0. So I have left with only this part, and I have to use the limit for this x, and with respect to y still we have, and we have to apply the limit here. By applying the limit, when I apply the upper limit, it is 1 minus y, then minus of lower limit is minus of 1 minus y, it becomes plus, so 2 times it becomes. So we left with only these terms, and integration of this, before that I have to multiply y square inside, so y square minus y cube dy. So this will be 2 into y cube by 3 minus y power 4 by 4, 0 to 1. So this is 2 into 1 by 3 minus 1 by 4, and lower limit is 0. This is 2 into LCM is 12. So 4 minus 3, which is 1. So totally this is 1 by 6. In the same way, we are going to take the second surface, that is double integral S2. So the first part what we have taken is I1. Now we are going to do I2. So for this, y square minus x into dx dy, which is same as the previous, dx dy, and the limit I have to see for this bottom region. So for this bottom region, when I take the horizontal strip, the x ranges from, I have to take from this equation. X will be minus 1 minus y, and from this x will be 1 plus y. So I can take the minus sign outside. So minus of 1 minus y, that is minus of 1 plus y to 1 plus y. When I take both the minus common, I get this as minus of 1 plus y. This is 1 plus y. And vertical limit, that is vertical limit for this region, it varies from minus 1 to 0. This is minus 1, and here it is y equal to 0. So we take, this is from minus 1 to 0. And again, first we have to evaluate with respect to x. So y square is a constant, so it will become y square into x. And again, this is an odd function, only x is there, so it is a odd function. So according to this, from minus a to a f of x dx will be 0. So after integration and using the limit, it will become 0. Once if we identify this odd function, so we can skip that part and we can put the limit only for the remaining term alone. So this is from minus of 1 plus y to 1 plus y. Still we have minus 1 to 0, and outside we have dy. When I apply the limit, upper limit minus of the lower limit, it becomes 2 times. So 2 y square into 1 plus y, we have minus 1 to 0, and we have dy. So now we are going to multiply this. So 2 into integral minus 1 to 0 y square plus y cube dy. So this is 2 y cube by 3 plus y power 4 by 4. We have from minus 1 to 0. By using the upper limit, we get everything 0, and using lower limit, we get minus 1 by 3 plus 1 by 4. So totally, this is 2 into, there is a minus sign outside. Let's take LCM, which is 12. This is minus 4 plus 3. So totally it is minus 1 by 12. There is a minus sign outside, so plus 1 by 12. So 2 into 1 by 12, which is 1 by 6. So in S1 surface, we got 1 by 6, and S2 also 1 by 6. So total RHS will become 1 by 6 plus 1 by 6, which is 2 by 6. After reducing, it is 1 by 3. So we got RHS as 1 by 3, and LHS already we got it as 1 by 3. So we find LHS and RHS are same. So LHS equal to RHS. Hence, Stokes' theorem is verified.